In 1856, a locomotive carrying 93 passengers crossed the Gasconade River in Missouri on a brand new wooden bridge. The bridge had been inspected that morning. It had been declared safe. 31 people died when the timbers gave way. The engine plunged 40 feet into the riverbed. Passengers were crushed beneath splintered wood and twisted iron. Bodies floated downstream for 3 days. And here is what happened next. They rebuilt the bridge, out of wood, and trains kept crossing. This is the part of American history that nobody wants to talk about. Before steel, before concrete, before engineering degrees and safety regulations, there was wood, just wood, exposed to rain and rot and fire, holding up locomotives that weighed 60 tons. And somehow, against every principle of modern engineering, it worked. And between 1850 and 1880, American railroad companies built over 30,000 wooden bridges. Some of them stretched 200 feet across open gorges. Some stood 150 feet above river surfaces. They swayed in the wind, they creaked under load. Engineers called them temporary structures while fully expecting them to last 20 years. They were building the impossible, and they were building it with axes, handsaws, and men who would never see their names in any history book. This is how America crossed every river, gorge, and valley on the continent using nothing but timber, rope, and the lives of workers who knew they might not survive the job. The year is 1850. You are standing on the eastern bank of the Mississippi River, and you need to get to California. Not eventually, not when it is convenient. Now, because there is gold in California, and every day you wait is a day someone else claims your fortune. Your options are limited. You can take a ship around Cape Horn. That is 18,000 miles and 6 months of ocean travel, assuming you survive the storms off the southern tip of South America. You can cross Panama, but that means yellow fever, malaria, and a jungle that has killed more travelers than the ocean ever did. Or you can walk. Most people walked. They loaded wagons, gathered families, joined caravans, and started the 2,000-mile journey across plains, deserts, and mountains. The journey took 5 to 6 months under ideal conditions. Conditions were rarely ideal. Roughly 10% of travelers died along the way. Cholera, starvation, native attacks, simple exhaustion. This was America in 1850. The nation stretched from the Atlantic to the Pacific, but it might as well have been 2 different countries. News from California took weeks to reach New York. Commerce moved at the speed of a walking ox. And then came the railroad. The concept was simple: lay iron rails across the continent, run steam locomotives on those rails, reduce a 6-month journey to 6 days, connect the coasts, unify the nation. The execution was anything but simple. Between the East Coast and the West Coast lay every geographic obstacle the continent could offer. Rivers that flooded unpredictably, gorges that dropped 500 feet straight down, mountain ranges that climbed to 14,000 feet, and none of it had bridges. To build a railroad, you first had to build a way across every single obstacle, every creek, every canyon, every marsh. And in 1850, you had exactly one material available that could be sourced, transported, and assembled fast enough to keep pace with track-laying crews: wood. Not because wood was the best option, because wood was the only option. Steel was expensive, scarce, and required foundries that did not exist west of Pittsburgh. Iron was heavy and brittle in cold weather. Stone took years to quarry and shape. But wood was everywhere. Forests covered the eastern half of the continent. The western half had enough timber in the Sierra Nevada and the Rocky Mountain foothills to build 1,000 bridges. More importantly, wood could be worked by hand. You did not need factories. You did not need specialized equipment. You needed axes, saws, and men willing to swing them 16 hours a day. This is where the story begins. Not with engineers in offices, with workers in forests. Picture a timber crew in 1858. Somewhere in the Appalachian Mountains, a railroad survey team has marked a route that requires a bridge across a 200-foot gorge. The gorge has a river at the bottom. The river floods every spring. The railroad needs to be operational by next summer. Someone has to cut the wood. A logging crew arrives in January. 12 men with axes and crosscut saws. They will spend the next 3 months living in a temporary camp, cutting timber in weather that regularly drops below zero. Their target is white oak. Oak is dense, rot-resistant, and strong enough to bear locomotive weight. A single bridge timber might need to be 30 feet long and 2 feet thick. That requires finding the right trees, felling them without splitting the wood, and dragging them out of the forest to a staging area. Felling a tree with an axe takes hours. The men work in teams, chopping from opposite sides, reading the lean of the trunk, calculating where it will fall. A miscalculation kills people. Trees do not fall predictably. They twist, they kick back, they hang up on neighboring trees, and come crashing down hours later when everyone has stopped paying attention. The men doing this work are not specialists. They are farmers, immigrants, laborers desperate for winter wages. They are paid $1 a day, which sounds reasonable until you calculate the cost of food, tools, and lodging that the company deducts from their pay. Most finish the season with less money than they started. Injuries are constant. A glancing axe blow to the shin, a finger crushed between logs. Frostbite that turns black by February. There are no doctors in logging camps. You either heal or you do not work. Men who cannot work do not eat. By April, the timber is ready. Thousands of board feet of white oak stacked and waiting. Now comes the harder part. Getting the timber to the bridge site. Rivers are the highways of the timber industry. Logs float. If you can get your timber to a river, you can move it hundreds of miles for almost no cost. The technique is called a log drive, and it is exactly as dangerous as it sounds. Workers roll logs into a river and ride the current downstream. They stand on the floating timber with pike poles, pushing logs away from banks, breaking up jams, keeping the mass moving. They do this in rivers swollen with snowmelt, water temperature barely above freezing, current strong enough to pull a man under and hold him there. Log jams are the real killer. Timber piles up against rocks or narrow bends, creating a dam of interlocked logs. Someone has to climb onto that jam and find the key log, the one holding everything together. Then they have to cut it free. When a log jam releases, it releases all at once, thousands of logs exploding downstream. If you are still on the jam when it breaks, you have about 2 seconds to jump clear. Many do not make it. Their bodies are found miles downstream, battered beyond recognition by the logs they were trying to free. The men who do this work are called river pigs. They are paid slightly better than logging crews, perhaps $1.25 per day. In exchange, they accept a mortality rate that would horrify any modern workplace. Estimates suggest that between 2 and 5% of river drivers died on the job each season. Think about that number. If you worked a log drive for 20 years, your odds of surviving were roughly even. The timber arrives at the bridge site. Now the real work begins. Building a wooden railroad bridge in the 1860s required a type of engineering that barely existed as a profession. There were no accredited engineering schools in America, no standardized formulas for calculating load-bearing capacity, no building codes, inspections, or certifications. What existed was experience. Men who had built bridges before, made mistakes, learned what worked, and passed that knowledge to the next generation. They called themselves bridge builders, and their education came from watching structures fail. The basic design for a wooden railroad bridge had not changed much since the Roman era. You build supports, called bents, that rise from the ground or riverbed to the level of the track. You lay beams across those bents to create a deck. You add bracing to prevent lateral movement, and you pray. The challenge is scale. A wagon bridge might span 40 feet and carry a load of 2 tons. A railroad bridge might span 200 feet and carry a locomotive weighing 60 tons, traveling at 30 miles per hour, generating dynamic forces that multiply the effective weight several times over. Wood is strong in compression. Stack oak timbers vertically, and they will support enormous weight. But wood is weak in tension. Pull on it, and the fibers separate. Bridges experience both forces simultaneously. The top of a beam compresses. The bottom stretches. Find the balance wrong, and the beam fails catastrophically. The bridge builders of the 1860s understood this intuitively, even if they could not express it mathematically. They overbuilt everything. Where one timber might theoretically suffice, they used 3. Where calculations suggested a bent could be spaced every 30 feet, they placed them every 20. This was not wasteful. This was survival. A wooden bridge was not a static structure. It moved, it breathed. Timbers expanded in summer and contracted in winter. Joints loosened over time. Individual members rotted at different rates, transferring loads unpredictably. A bridge that seemed solid in May might develop dangerous flex by October. The builders knew this. They built bridges expecting them to degrade from the moment of completion. The massive timbers, the redundant bracing, the seemingly excessive number of bents, all of it was insurance against the inevitable decay. Now picture the construction site. It is June 1860. You are standing at the edge of a gorge in central Pennsylvania. The gorge is 180 feet deep. The river at the bottom floods to 20 feet above normal every spring. The railroad needs a bridge across this gorge, and they need it before winter. You have 6 months. The first task is building falsework. This is the temporary structure that supports the permanent bridge during construction. You cannot simply start building a bridge from one side and work toward the other. The weight would be unbalanced. The incomplete structure would collapse. Instead, you build scaffolding from the bottom up. Workers descend into the gorge on rope ladders. They clear the riverbank, level the ground, and begin assembling a wooden tower that will eventually reach 180 feet into the air. The falsework is built from the same timber that will become the bridge. It is assembled with wooden pegs and iron bolts, braced against the gorge walls, and designed to be dismantled once the permanent structure is complete. Climbing the falsework is a daily routine. Workers ascend ladders lashed to the scaffolding, carrying tools, hardware, and sometimes individual timbers on their backs. There are no safety harnesses, no nets, no fall protection of any kind. A man who loses his grip falls until he stops. Falls are common. Some are fatal, others result in injuries that end careers. A broken leg heals wrong and leaves a man crippled for life. There is no compensation, no disability payment. You simply stop receiving wages. The company might send your personal effects to your family if someone remembers your address. As the falsework rises, the permanent bridge takes shape on top of it. The main support timbers are hoisted into position using block and tackle rigged to the scaffold structure. Each timber is hand-fitted, the joints cut with chisels and saws until the pieces lock together with structural precision. The joints are the critical points. A bridge is only as strong as its connections. The builders use a combination of techniques. Mortise and tenon joints, where a projecting tongue fits into a corresponding hole. Lap joints, where 2 timbers overlap and are bolted together. Scarf joints, where timbers are spliced end to end to create lengths that would be impossible to cut from a single tree. Each joint is a potential failure point. Water infiltrates. Freeze-thaw cycles work the bolts loose. Insects find their way into the exposed wood grain. A joint that tests solid in year 1 might crumble to powder in year 5. The builders know this. They specify heartwood, the dense center of the tree. For all structural joints, they coat exposed surfaces with linseed oil or tar. They design drainage channels to prevent standing water. And still, the bridges rot. A wooden railroad bridge has a working lifespan of roughly 15 to 25 years. Some last longer, many last far less. The railroad companies plan for this. They budget for replacement. They accept that every bridge on their line will need to be rebuilt within a generation. This is the dirty secret of 19th century railroad engineering. Nothing is permanent. Everything is temporary. The only question is how long the temporary solution will last. By September, the bridge across the Pennsylvania Gorge is complete. 180 feet tall, 220 feet long, built from white oak timbers, some of them 30 inches square, held together with iron bolts that weigh 50 pounds each. The first locomotive crosses on September 14th. The bridge sways perceptibly under the load. The engineer reports hearing creaking from the support structure. The bridge company marks the crossing as successful. 3 years later, the same bridge will require emergency repairs after a bent fails during a spring flood. The repairs take 2 weeks. During those 2 weeks, the railroad loses approximately $40,000 in revenue from trains that cannot cross. The company does not question whether the bridge should be rebuilt in steel. Steel is still too expensive, too scarce, too difficult to work. They repair the wooden bent with more wood. They reinforce the damaged joints. They return the bridge to service and hope it survives until they can afford to replace it. This is the rhythm of American railroad construction. Build fast, build cheap. Fix it later. The workers who build these bridges develop a particular set of skills. They can look at a timber and tell you whether it will bear weight or split under load. They can judge the angle of a brace by eye, calibrating forces without calculations. They can climb 100-foot structures in wind and rain, swinging from beam to beam with a confidence that borders on insanity. They also develop a particular attitude toward death. A bridge crew working a major construction project will typically lose 1 to 3 men over the course of a building season, sometimes more. The causes are predictable: falls from height, crushing injuries from dropped timbers, drowning during foundation work, occasionally structural collapse. The survivors do not stop working. They cannot afford to stop. A day's wages lost is a day's food that will not reach their families. Grief is a luxury reserved for those who can survive without labor. What develops instead is a kind of fatalism, an acceptance that some men will die and others will not, and there is no predicting which category you will fall into. The only control you have is your skill. Work carefully, trust your instincts, and never assume that any structure is safe just because someone else says it is. The men develop superstitions. Never whistle on the job. Never step over a timber twice. Never be the last man to leave a completed structure. These beliefs are irrational, but they provide a framework for coping with randomness. If you follow the rules and survive, the rules must be working. There is also drinking. Considerable drinking. Whiskey is cheaper than medicine and more reliable for numbing the pain of injuries that cannot afford proper treatment. A man with a whiskey habit can still work. A man with an untreated infection cannot. The railroad companies tolerate the drinking as long as productivity continues. They do not tolerate strikes, union organizing, or complaints about conditions. Workers who make trouble find themselves blacklisted, unable to get work anywhere on the line. The message is clear: accept the conditions or starve. This is the human cost of progress, measured in broken bodies, shortened lives, and families that never see their fathers return. The wooden bridges they build stand as monuments to this sacrifice. Every beam was cut by hand. Every joint was fitted by men who could feel the grain of the wood through their calluses. Every bolt was hammered into place by workers who knew they might fall before the job was done, and the bridges worked. That is the remarkable thing. Despite the primitive tools, the absent engineering theory, the impossible deadlines, the bridges carried trains. They connected cities. They unified a nation that would have remained fractured without them. The most impressive wooden railroad bridges were the trestles. A trestle is essentially a series of connected frames, each supporting a section of track, stretching across a valley or marsh like a wooden centipede. The principle is simple. Instead of building one long span, you build many short spans supported by many bents. Each bent carries only a fraction of the total load. The structure is redundant. If one bent fails, the neighboring bents can potentially absorb the additional stress while repairs are made. In practice, trestle construction pushed the limits of what wood could do. Consider the Portage Viaduct in New York, completed in 1852. 800 feet long, 234 feet tall at its highest point, built entirely from wood. It was, shut for a time, the largest wooden bridge structure in the world. The numbers are staggering. Over 1 million board feet of timber, 300,000 pounds of iron bolts and hardware. Construction took 18 months and cost approximately $175,000, which was an astronomical sum for the era. The viaduct stood for over 2 decades before fire destroyed it in 1875. During those decades, it carried every passenger and freight train that crossed the Genesee River Valley. It swayed visibly when trains crossed. Passengers reported feeling seasick from the motion, and it never collapsed. This was the genius of American wooden bridge engineering. Not theoretical elegance, but practical resilience. The structures were ugly by classical standards. They used 10 times more material than a mathematically optimized design would require. But they survived floods, fires, overloaded trains, and decades of minimal maintenance. The European engineers who visited America in the 1850s and 1860s were appalled. They saw the wooden bridges as primitive, wasteful, embarrassing evidence of American technological inferiority. Their stone viaducts in France and England were architectural masterpieces. American bridges looked like oversized children's toys. What the Europeans failed to understand was context. France had been building infrastructure for 1,000 years. England's railway network covered a few hundred miles. America needed to build 30,000 miles of track in 30 years, across terrain that made European geography look like a garden path. There was no time for elegant engineering, no budget for carved stone, no workforce trained in precision masonry. There was wood, sweat, and desperation, and somehow it was enough. The trestle builders developed techniques that would not appear in engineering textbooks for another 50 years. They understood, through trial and error, how to distribute loads through three-dimensional wooden frames. They knew how to brace against wind loads that could exceed the weight of a locomotive. They learned how to design joints that would tighten under stress rather than pulling apart. This knowledge was passed from crew to crew, foreman to apprentice, through demonstration rather than documentation. A master bridge builder could not explain the physics of what he was doing. He could show you. He could watch your work and tell you whether it would hold. He could walk onto a completed structure and know, by the feel of it under his feet, whether it was safe. This intuitive engineering was the product of countless failures. Every collapsed bridge taught a lesson. Every fatality revealed a weakness in the design. The builders who survived longest were the ones who learned fastest. By the 1870s, the accumulated knowledge of wooden bridge construction had reached its peak. The builders could design and construct structures that would have seemed impossible just 20 years earlier. Spans of 300 feet, heights of 250 feet, load capacities that exceeded the heaviest locomotives in existence. And it was already becoming obsolete. Steel was coming. The Bessemer process, patented in 1856, made it possible to produce steel in quantities and at prices that had previously been unimaginable. By the 1880s, steel bridges were replacing wooden structures across the American railroad network. The transition was gradual but relentless. Wood rotted, wood burned. Wood required constant maintenance and eventual replacement. Steel rusted, but slowly. Steel did not burn. Steel, once erected, could stand for a century. The wooden bridge builders watched their profession disappear. The skills they had spent decades developing became worthless. The intuitive understanding of timber, the ability to read the grain and judge the strength, none of it applied to steel. The craft died with the generation that practiced it. Today, almost nothing remains. A few preserved trestles in railroad museums, some rotting bents visible in the woods along abandoned rights of way, photographs that show wooden towers climbing impossibly high against mountain backdrops. And statistics, always statistics. Approximately 3,000 men died building the Transcontinental Railroad. Many of those deaths occurred during bridge construction. Falls, collapses, drownings, crushing injuries. Each death is a line in a ledger somewhere, if it was recorded at all. Chinese workers, who made up the majority of the Central Pacific's construction force, were often not counted. We do not know their names. We do not know where they were buried. We know only that they existed, because the bridges they built still appear in photographs, and someone had to build them. This is the debt we rarely acknowledge. Every time you use the infrastructure of this country, you are benefiting from work that killed people. Roads, bridges, railroads, tunnels. All of it was built by human hands under conditions that would be considered criminal today. The workers who died made our lives possible, and we have forgotten them so completely that we do not even know we should be grateful. The wooden railroad bridges are gone now, replaced by steel, then concrete, then advanced composites. Each generation of materials more durable than the last. each generation requiring fewer workers, fewer injuries, fewer deaths. This is progress, this is what we celebrate, and it is worth celebrating. The conditions that killed bridge builders in the 1860s were not acceptable then, and they are not acceptable now. We should be glad that workers today have protections that their predecessors lacked. But we should also remember the comfortable world we inhabit was purchased with suffering we prefer not to imagine. And the bridges we cross without thinking were preceded by bridges that swayed in the wind, built by men who knew they might not survive the season. They built them anyway. That is the story. Not engineering triumph, although there was triumph. Not American ingenuity, although there was ingenuity. The story is human beings pushing the limits of what their bodies could endure, taking risks that seem insane in retrospect, dying by the thousands so that trains could cross rivers. The bridges they built were temporary. The bridges were always temporary. Everything they built has been replaced by something stronger, safer, more permanent, but the men were real. The work was real. The deaths were real. And for one brief period in American history, before steel made it unnecessary, before machines made it possible, and human beings built 200-foot bridges out of wood, they built the impossible, and then they were forgotten. The last of the great wooden railroad trestles burned or rotted away by 1920. The last of the men who built them died by 1940. The knowledge they carried, the intuitive understanding of timber and force and risk, died with them. What remains is the network they created, the routes they established, the connections they forged between cities that had been weeks apart. We still use those routes today. We still follow the paths they cut through mountains and across valleys. Every train that crosses America follows a path that was first bridged with wood. The steel bridges and concrete viaducts stand where wooden trestles once stood. The ghosts of those temporary structures are built into the permanent geography of the nation. We do not see them. We do not think about them. We board our trains and cross our bridges and never consider how any of it became possible. But they were there. The timber crews who cut the logs in winter, the river pigs who floated them downstream in spring, the bridge builders who assembled them in summer, the workers who died in every season. They were there, and they made this country possible, and we owe them more than we will ever repay. The next time you cross a river on a bridge, any bridge, remember, there was a time when crossing that river meant risk, when every bridge was a bet against failure, when the men who built bridges knew that some of them would not live to see the other side. They built them anyway. That is the inheritance we carry. That is the debt we owe. Not to the engineers who designed the bridges or the companies that financed them, to the workers who climbed the scaffolding, knowing the risks, building the impossible anyway. 200 feet tall, made of wood, swaying in the wind, they built the impossible, and then they were forgotten. But not by everyone, not anymore. If this is your first time here, consider subscribing. I cover the forgotten stories of the workers who built this country, the dangerous jobs, the impossible projects, the human cost of progress that the history books leave out. I will see you in the next one.